Good morning, students. During the last 3 months, we discussed about the different chapters of organic chemistry: haloalkane, haloarine, alcohol, phenol, ether, aldehydes and ketones, monocarboxylic acids, amines. Also, we discussed polymers, chemistry in service to mankind, and in physical chemistry, we discussed about the chemical kinetics. Now, in the coming classes, we will have a revision chapter wise. Haloalkane, haloarine will have one revision chapter. Then also we will discuss about the alcohol, phenol and ether. Then another video will be on the aldehydes and ketones and monocarboxylic acid, and the one for amine. Then polymer and chemical service mankind. And finally, also we will have a class on the chemical kinetics. So each one video will have one chapter. Okay. So now today we will discuss about the haloalkane and haloarines. Okay. Now the first thing, what are the important points, important things that we have to emphasize on this chapter haloalkane and haloarine. First of all, we have to practice the methods of preparations of haloalkanes, and secondly, also we discuss about the chemical properties of haloalkanes, methods of preparation of haloarines, chemical properties of haloarines. We discuss the important properties and important preparations. Okay. And also we discuss about the topics, important name reactions that we have to emphasize, like Hans-Rediker reaction, like Finkelstein's reaction, like Schwarz reaction, Sandmann's reaction, Gattermann's reaction, Wood reaction, and Fittig reaction. Now also your Wood-Fittig reaction, Wood-Fittig reactions. Also we have Bas-Kamen reaction. Okay. SN1 and SN2 reaction, short nose, SN1 SN2 reaction. In addition to this also, we'll focus on basically different examples of SN reaction and also about what the elimination reaction. So these are the different topics of haloalkane and haloarenes that we will discuss today. Okay, briefly the important points we will discuss and also we will discuss some questions based upon these facts. Okay, first of all, methods of preparation of haloalkane. Okay, now you can note down this. You can note down these topics, and these are the important things that will be asked in the examination. Host decay reaction, Euclidean reaction, Schwarz reaction, Sandwich reaction, Gatterman reaction, Wood reaction, and Fittig reaction, and also Bosch-Kamen reaction, and SN1 and SN2 reaction. So these are the important areas from where the typical questions will be asked. Either write short notes on SN1 and SN2, or you can say write about the chemical reactions. Any one or two or three reactions will be there. Write about the reactions. Okay. So this name reactions are the most important. We have to practice more and more. Okay. And we will discuss one by one. No problem. Okay. Now methods of preparation of haloalkane. Okay, let's see how the haloalkanes can be prepared in different methods. Okay, see, so this is the complete preparation of haloalkanes. How we can prepare haloalkanes? From alcohols, from alkane, from silver salt of acid, from alkene. So this is the summary. Let's see, suppose I have taken the typical haloalkane, that is ethyl bromide. How can I prepare ethyl bromide? Okay, so I can prepare ethyl bromide from ethane simply by boiling the ethane with bromine. Okay, so when ethane is boiled with bromine, then ethyl bromide is formed. Also, we can prepare by with your HNU. If I suppose CH3, I can plus Br2, HNU. Also, I can get value CH3, CH2, Br. Okay, so ethyl bromide can be prepared from ethane by boiling with your bromine. And if you prepare suppose your chlorine, suppose I prepare your ethyl chloride or methyl chloride, I can take methane plus Cl2 HNU, I can get CH3Cl. And that on excess of chlorine, this methyl chlorides again will convert to dimethyl chloride, that is C2Cl2, then again your CH3, finally your CCl4. So if you take methane CH4 plus Cl2 with HNU, then all the hydrogens can be replaced by the chlorine atoms to give you mono, di, tri and tetra halogen derivatives. Okay. Now same ethyl bromide also I can get from ethene. From ethene and alkene, on addition of HBr, I am getting what ethyl bromide. So when HBr is added to ethene, then ethyl bromide is formed. We can take an alkene and HBr. What happens? This pi bond will break. So 1 to 1 carbon your H will be attached, and other carbon bromine will be attached. That means HBr will be added across the carbon-carbon double bond to form the haloalkanes. But here you see, this is a symmetrical alkane, C2 C2. So I am simply getting ethyl bromide. Now here I I have an unsymmetrical alkane like this one. See, CH3, CH double bond CH2. This is an unsymmetrical alkane. So here, if I add HBr, then I have to follow what rule? Marconi-Kopso rule. We know the Marconi-Kopso rule. When an unsymmetrical reagent is added to an unsymmetrical alkene, then the negative part of the addendum will go to the carbon having less number of hydrogen atom. So here, this carbon double bond, this carbon is having 1 H, this carbon is having 2 H. So when I will add HBr, the bromine atom will be attached to this carbon. I will get what? C3, C2, Br, C3. So here I will apply Marconi-Kopso rule. Now for the same unsymmetric alkene, if I will add HBr in place of peroxide, then what will happen? The anti-Marconi-Kopso rule will be applied. That is what the negative part will go to the carbon having a high number of hydrogen. This will be again Ca3, Ca2, Ca2, Br. So there may be questions. Suppose propane is there, HBr, peroxide, write the major product. So whenever an unsymmetric alkane is there, so we can find out the major product by applying Marconi-Kopso. Okay. This is the way how can you prepare halo alkanes from your alkanes. So this is simply it is not HBr, but this is what it is some HBr, the Marconi-Kopso rule. Okay. When some peroxide, again addition with your anti-Marconi-Kopso. Okay. Now again, I can get this ethyl bromide from alcohol. From alcohol, I adding what HBr. For this HBr, I can get from NaBr and H2 support. From NaBr and H2 support, so I will get NaBr support and HBr. Now this HBr will be added to C3, C2 also, and we get what ethyl bromide. Again, this from alcohol by adding PBr3, I can also get value C3, C2Br. For this PBr3, I have to take from red P and bromine. So when I take red phosphorus with the bromine, so from this I will get PBr3. This PBr3 will react with your ethyl alcohol to give what ethyl bromide. Similarly, I can get the ethyl bromide from your silver salt of acid. CH3COOH is there, so C3COOH when added with bromine plus of C4, then we get value C3CH2Br plus AgBr. So then so from silver salt of acid, so if I take CH3, this is CH3 CH2 COOH. Okay, so C3CH2 COOH, I will get value C3CH2Br plus CO2 plus AgBr. Okay, so here this silver salt of carboxylic acid when it with your bromine in C4, then we are getting what C3CH2Br. This is called Hans-Dicker reaction. This is called Hans-Dicker reaction. So getting also formation of halo alkane, alkyl bromide from silver salt of carboxylic acid in place of bromine and C4, this is called Hans-Dicker reaction. Okay. Now, then after we can prepare the fluoroalkane, alkyl fluorides from the alkyl bromide. From this alkyl bromide, ethyl bromide, if I take what AgFO, I will heat, then I can get what C3C2. This you see from ethyl bromide, I am preparing the ethyl chloride. Okay, so when ethyl bromide is heated with the silver chloride, then your ethyl chloride is formed. This is called Schwarz reaction. Now, similarly from the ethyl bromide, when the ethyl bromide is heated with the NaI in presence of acetone, then the ethyl iodide is formed. This is called Finkelstein reaction. This is also called iodide exchange reaction. So, and this is also I can take chloride. So when chlorides or bromides are heated with or sodium iodide in presence of acetone heated, then I am getting the alkyl iodide. This is called Finkelstein reaction. Okay. So this is about the what your preparation of your ethyl bromide from your ethane, from ethyl alcohol, from ethane, from your silver salt of acid. Okay, and also how to prepare these fluoro and iodoalkane from the bromoalkane. From the bromoalkane by heating with the AgFO, I can get your fluoroalkane called Schwarz reaction, and from your alkyl bromide by heating with your sodium iodide and acetone, I can get the alkyl iodide called what your Finkel-Stensel reaction. So if questions will ask you what is Finkel-Stensel reaction? So this is an iodide exchange reaction, so where an alkyl bromide is heated with the NaI in presence of acetone. Okay. And also, if a question asks what is your Schwarz reaction? Schwarz reaction is the formation of alkyl fluoride from alkyl bromide. When ethyl bromide is heated with the AgFO, okay, then your ethyl fluoride is formed. This is known as the Schwarz reaction, and we can write the equation. Okay. Now, similarly, also you can prepare ethyl chloride. Same thing, so you can prepare from ethyl alcohol. From ethyl alcohol, by giving concentrated HCl and the anhydrous Cl2, we can prepare what is the alkyl chloride. And we will see this concentrated HCl and anhydrous Cl2 is called what Lucas reagent. Concentrated HCl and anhydrous Cl2 is called what Lucas reagent. Now, when alcohols are reacting with the Lucas reagent, then haloalkanes are formed. But remember here, so here the different alcohols are having different actions on this Lucas reagent. So when primary alcohols are reacting with the Lucas reagent, we are getting the haloalkane. And also when secondary alcohol is Lucas reagent, we can get same haloalkanes, and also in tertiary. So along with what is formed. But here, when we have the primary alcohol, so the haloalkanes is obtained. Then after cloudiness is appearing, and that cloudiness appears after heating. Okay, but in case secondary alcohol, if you take a secondary alcohol, then the haloalkane will form, and a cloudiness will appear after 5 minutes. Okay, and whereas if you have taken tertiary alcohol, then the cloudiness will appear immediately. So by using this Lucas test, we can distinguish between the primary, secondary, and tertiary alcohols. Okay. So what is Lucas? Question may be there. What is Lucas reagent? It's what you know. It's a mixture of concentrated HCl and anhydrous Cl2. Now, what is the order of action of Lucas reagent towards alcohols? Okay, so your tertiary alcohols are more reactive than secondary alcohol than your primary alcohol. Okay, so this is how to prepare your alkyl chloride from the alcohols. Now also we can prepare this alkyl chlorides from the alcohol by using your PCl3. When you take PCl3 phosphorus trichlorides, then we will get C3Cl2Cl and H3PO3 will liberate. Similarly, also we can take C3Cl2O2 and PCl5. Here I can get C3Cl2Cl and plus POCl3 plus HCl. Okay. And also we can prepare this by taking SOCl2. You can get C3Cl2Cl plus SO2 plus HCl. Now in this case, whether PCl3, PCl5 and SOCl2 is the more convenient method of getting alkyl chlorides from the alcohols. So there will be questions: which of the following is the most suitable for getting a haloalkane from alcohol? PCl5, PCl3, SOCl2. Then what is the answer? Answer is SOCl2. SOCl2 is the, because when I am taking SOCl2, I am getting SO2, which is a gas, and HCl. So we can easily get this alkyls, which will be difficult in case of PCl3 and PCl5. Okay, so along with PCl3, PCl5 and SOCl2 is a more convenient reagent of getting haloalkanes from the alcohols. Okay, so these are all about methods of preparation of halo. And you will see this is the addition of electrophilic addition. This is an electrophilic addition reaction here. You see. Okay, and this electrophilic addition reaction is followed by Marconi coupling. Then we have the unsymmetrical alkane. Okay. And if we have the unsymmetrical and peroxide, then we are following what anti-Marconi couple, also called your cross peroxide effect. Okay. Now next we will go to about your chemical properties of your haloalkanes. Okay. So these are the chemical properties of haloalkanes. So first I will study here the nucleophilic substitution reactions. You know haloalkanes are X, okay? You will see the CX, the CX bond is your polar. So because the CX bond is polar, the X can with the electron pair was keto can carries a negative charge. Now C becomes a positive charge. Now to this positive carbon center, a nucleophile can easily attack, and we know the halogens are the better living groups. So they can live as a living group, and the nucleophile will attach to the carbon. Okay, so CX is there, nucleophile will attack, then X will go as a living group, and will get value is the product. Now different nucleophiles can attack to this haloalkanes to give different products. Let's see here. If I take suppose KOH is the nucleophilic reagent. And here the OH minus is the nucleophile. If I take C2H5Br, ethyl bromide with aqueous KOH will boil, what happens? You get C2H5OH plus KBr. So what happens here actually? The C2H5Br, okay, now this Br go out as Br minus as the living group, and OH minus as nucleophile attached to this carbon. Okay, so I am getting what C2H5OH. So OH is the nucleophile here. Br minus is also nucleophile. The OH minus ion is the better nucleophile than the Br minus. So the OH minus replaces the Br minus, and we are getting what the ethyl alcohol. Okay, so when we will be aqueous KOH. Similarly, if I take C2H5ONA in the reagent, I will get what C2H5O minus. Okay, ethoxide ion. Now this one is the nucleophile. So when I have ethyl bromide with what with sodium ethoxide, so from here Na plus and C2H5O minus. So the C2H5O minus is the nucleophile, which is a better nucleophile than the Br minus. So this will replace this Br minus, and we get what C2H5O. C2H5 is called what ether. And this reason of getting your ether from haloalkane with the help of sodium alkoxide is called Williamson reaction or Williamson's ether synthesis. Okay, so haloalkanes when made with your sodium alkoxide, okay, sodium alkoxide, then what ether is formed. This is called what Williamson's reactions. Okay, here you see ethyl bromide is reacted with what sodium ethoxide to give what diethyl ether, which is called what Williamson reaction. Similarly, I can take C3CONA. So where I will get what C3CO minus CO minus is the nucleophile, and when this C2H5 will lead to C3CONA, then what you see Br minus will be replaced by the C3CO minus, and we will get what C3CO C2H5 or ethyl acetate. So I will get an ester. Okay, so ester can also be prepared from this haloalkanes. Okay. If I take ammonia, then ammonia NH3 is a nucleophile. Now here C2H5Br plus NH3 will get what C2H5NH2, that is amine. But here if you take excess ammonia, so now this C2H5 the C2H5NH2 again I will take with your alkyl bromide. So C2H5NH2 plus C2H5Br again I will get what C2H5 whole 2 NH2 secondary amine. Again, if I take C2H5Br, C2H5 whole 3 NO, I will get tertiary amine. So this NH3, the hydrogens will be replaced by the alkyl groups to form primary, secondary, and tertiary amines. Okay, this is also called ammonolysis. Okay, so alkynes are the same. Now, if I have KCl, from this I can get Cn minus ion is the nucleophile. Cn minus is the nucleophile, and here when ethyl bromide is alcoholic cation, when get to the alcoholic cation, then this bromide Er minus the nucleophile will be replaced by the Cn minus nucleophile to get value C2H5Cl. Okay, now this is C2H5Cl. I will write some bases of C2H5Cl. You see, so when I have this RXO, see C2H5Br, okay, or if I take R, suppose if I take RXO, see RXO plus your KCl alcoholic, okay, I am getting what heat, remember RCl. Now this from this RCl, if I go for acidic hydrolysis from RCl, I will get value RCOOH. So this cyanide can be converted to value carboxylic acid. Again, this RCl I can also undergo reduction if I go for sodium and alcohol. Okay, I will get RCH2NH2. So I can reduce the cyanide into amine. Now so this Cn, if I go for alkaline hydrolysis H2O2 OH minus, I can get value RCONH2. So this cyanide can be converted to acid into amide into amine. So this kind of this reactions will be very much useful for the conversion reactions. Suppose someone question will ask you, convert methane into acetic acid. Convert methane into acetic acid. How can you do this? Do this, you see. If I say convert methane into acetic acid, you can say your methane, CH4 methane, okay, and Br2 boil. We get what? CH3Br. Now give your KCl, what do? CH3Cl. Now give what do? H2OH plus. We get what do? CH3COH. So methane can be converted to acetic acid with the help of how do? This is cyanide reaction. So okay, first methane into methyl bromide, then methyl bromide to methyl cyanide, then into acid. Okay, similarly we can convert methane into amine also. Okay, so CH4 Br2 boil, what do? CH3Br, then give your KCl, CH3Cl. Now then what do? Reduction, we get what? CH3 CH2NH2. Again, this amine you can give your HONO to get what do? The ethyl alcohol. So methane can be converted to ethyl alcohol. Okay. So if I can convert methane into ethyl alcohol, see methane CH4 Br2 boil CH3Br, okay, and KCl, CH3Cl, then reduction sodium alcohol, CH3 CH2NH2, then HONO CH3 CH2OH. So this methane can be converted into ethyl alcohol. So with the help of this cyanide reaction, so we can convert one compound to the other compound with your step off. So here one carbon, here two carbon. Okay. So this is the application of these reactions. Okay. So questions may be asked. Now similarly, if I take HCl, okay, here the NC minus will be your nucleophile. You get value isocyanide. Similarly, AgNO2, here the NO2 is the nucleophile here, and we are getting C2H5NO2. Then if I take NaNO2, and I get what ON, nitrate. Okay, so these are the nucleophilic substitution reactions shown by haloalkanes. Also see how alkanes are also showing what you elimination reaction. You will see CH3CH2Br ethyl bromide by your alcoholic then what will get your alkene. So CH3 CH3 CH2Br plus K alcoholic will get what H plus Br minus okay this one will get what CH2 double CH2 plus KBr plus CH2. That means see this called also what dehydrohalogenation. So one hydrogen and one halogen is removed here called what dehydrohalogenation. Now this dehydrohalogenation when taking place in water in symmetrical alkenes say no problem in symmetrical haloalkane, so then we are just removing the H. But when it is your unsymmetrical, suppose I have the CH3 CH2 Br CH2 CH3. So here you see this bromine added to carbon. Now this carbon is having 3 hydrogen, this carbon having 2 hydrogen. Okay, so now I can remove the hydrogen from this carbon or from this carbon. Accordingly, I will get 2 products. So one will be major, one will be the minor. So you see, I can write your CSO2, double bond CH2, single bond CH2, single bond C3, or I can write your CHO3, CH double bond CH2, single bond CH3. This is called your setup product. Okay, your major. This is what you minor. So whenever and this is called hydrogen, this is called beta elimination. We are eliminating the hydrogen from the beta carbon. So whenever beta elimination will take place, okay, the hydrogen atom will be preferentially eliminated from that carbon which have less number of hydrogens, so that we will get a more substituted product which is more stable. You will see, if I remove the H from this carbon having more hydrogens, I am getting this one. If I remove the H from this carbon having less number of hydrogens, I am getting this one. And this species is having what? More number of alkyl groups or substitutes, and this is your more stable. This is called what? Self rule. Okay. So elimination in unsymmetrical alkenes is taking place with the help of Self rule. Okay. So there will be questions, write the major product. Okay, so here we will say what the major product will be what as per the Self rule. Okay. Suppose I have CH3, CH2, CH double CH2. This is what but1 ene. but1 ene. Now you convert into what CH3, CH double CH2, CH3. But 2 ene. But 2 ene. Now how can you convert? You see, CH3, CH2, CH double CH2. Now take HBr, okay. You get what? CH3. So you will see there will be a Marconi co because these are unsymmetrical. You get what? CH3, CH2, CH2, Br, CH3. Okay. Now again you give what? A was alcoholic. Okay. So this is your CH2, this is your CH3. So how you set the rule? Okay. You get what? CH3, CH double CH2, CH3. So here what? Marconi co. Here what? Set. Okay. So in this way we can convert due to 1 ene into due to 2 ene. Okay. And these are what are the chemical properties of the haloalkanes, the substitution reactions, and the elimination and the elimination reaction. Okay. Now so we have the reaction with Grignard's reaction with magnesium metal. Then we are getting what is the Grignard's reagent. You see, if I have RXO plus Mg dry ether, I will get value RMgX. Okay, this is called value Grignard's reagent. And this Grignard's reagent is having many applications. Okay, so haloalkanes react with magnesium metal in presence of a dry ether to give value Grignard's reagent. And this Grignard's reagent is having many synthetic applications. So from this Grignard's reagent, I can if I take suppose HOH, I can get value RH plus MgOH. Okay. Now so from this RMS, if I give you alcohol, if I take value C3OH, R-OH. Okay, I will value RH plus R-OH. So on this Grignard's reagent, by giving your water, you can prepare alkane. Giving your alcohol, you can prepare your alkane. Now so from this Grignard's reagent, by taking your aldehydes, you can prepare alcohols. Okay, so if you take some your formaldehyde, with this Grignard's reagent, you can get your primary alcohol. Take other aldehydes, you can get secondary alcohol. Okay, and if you take ketones, you can get your tertiary alcohols. So you can prepare alcohols also from Grignard's reagent, and also by taking this, we can prepare the carboxylic acid. Many applications are there. Okay, of the Grignard's reagent. Okay. So these are the some typical relations of haloalkanes. Okay. Now the question is what happens when, or how can you obtain, how can you convert, will basing upon all these relations. Okay. Now this the nucleophilic substitution reactions shown by the haloalkanes can be of two kinds. One SN1, SN2, and SN1. Okay. So SN2 and SN1 are the nucleophilic substitution reactions shown by haloalkanes. Okay. Now see, SN2 is what substitution nucleophilic bimolecular. Is what substitution nucleophilic bimolecular, and this is what substitution nucleophilic unimolecular. Okay, here what molecularity 1, order 1. Here sorry, molecularity 2, order 2. Here what molecularity 1, order 1. Now you see this reaction, the substitution nucleophilic bimolecular, here the rate of the reaction depends upon two things. One is the nucleophile and other is the concentration of the substrate molecule or the reactant. But here is the SN1, the rate of the reaction depends upon only the substrate. Okay, so here what is rate sound value nucleophile and what substrate, and here rate was on what only substrate. Okay. Now in this this is what this is a one step reaction. This is what two-step reaction. Okay, so SN2 is a one-step reaction and SN1 is a two-step reaction. Okay, now you will see here, if I have suppose H C H H was Br, and when I have the nucleophile, when I have the nucleophile is the negatively charged nucleophile or maybe neutral but contains electron deficient species. So when this negative nucleophile or the nucleophile having electron efficient center is coming towards here, because this Br is having a negative charge, it is a negative species, so it will not allow the nucleophile to attack from this side. So what happens? The nucleophile will come and attack from the left side. So in SN2 reaction, so back attack takes place. The nucleophile is always attack 180-degree opposite to the leaving group. So when from the opposite side the nucleophile will attack, so now this this bromine nucleophile will leaving group will go out and will get what the HOC H. So this is called what inverse Napu configuration. In SN2 what inverse Napu configuration takes place. What inverse Napu configuration, and because of this the nucleophile is attacking from this back side, the inverse Napu configuration takes place. Okay, and the order of the reaction is what primary or more reactive, then secondary, then tertiary. Because here the nucleophile is attacked from the back side. If already the alkyl groups are present in this carbon atom, so the bulkier alkyl groups will not allow this nucleophile to attack the carbon easily. That will cause steric hindrance. Okay, so presence of alkyl groups will cause steric hindrance. That's why the order of reactivity of primary haloalkane is more than secondary, then tertiary. So the main question is which of the following will respond better to the SN2 reactions. So if I have ethyl bromide, okay, suppose I have the a secondary suppose CH3 CH2 Br, CH3 Br, so CH3 Br, and what happened? The CH3 CH2 Br will be more reactive, then C3 Br, then C3 Br. That is your tertiary. Okay, so that may be a question. That may be a question in the exam. So which of the following will respond to more to SN2 reactions? Okay, that you can decide. See, if the primary is there, that will respond to more. So here you can say this is a two-step reaction. So what happens here? First of all, if I have suppose R1, so R1, C, R2, R3, and X is there. Okay, so here in case of SN1 reaction, SN1 is a two-step reaction. So okay, now if the alkyl halide which we have taken is a optically active alkyl halide, so then what happens? So the mixture of two products will obtain one your retention of compression or your inverse of compression. Okay, that will get racemic mixture. So in that case, the nucleophile can attack from the front side, also from the back side. Okay, you will see. So this is first of all, this is slow step. Okay, so R1, C R2 R3 plus. So carbon catalyst is formed. In the first step, a carbonium ion will be formed, and now this carbonium ion I have R1C R2 R3 plus. Now I have the nucleophile here. On back side, you get value NuC R2 R1 R2 R3. Okay, this is what you know. Inversion of confusion, inversion, and on the front attack, you get value the R1C R2Nu R3. Retention. So retention of conversion and inversion of conversion both will take place. Okay, so here. So and here the order of reactivity, because I am getting a carbonium ion in the intermediate. Okay, because I am getting a carbonium ion intermediate. So now the tertiary carbonium ion is more stable than secondary than primary. That's why the tertiary carbonium tertiary alkylic acid will be more preferred towards the SN1 and SN2. So here are one level, the reactivity is what? Reactivity is tertiary more reactive, then secondary, then primary. So this is a short note question, 3 mark. Okay, important. This is an important one. Okay, write short notes. Okay. Important for what? 3 mark. Write short notes on SN1 and SN2 reaction mechanism. Okay, so you just write the differences and the distance. Okay, that is called what? The difference between SN1 and SN2 distance. Okay, now next come to the halo elements.